Welcome dear students. Welcome to yet another lecture on transmission line theory. This is a lecture on Smith chart basics. In this lecture I am going to cover one of the most important topic of Smith chart, which is understanding a plot of load impedance versus input impedance in a Smith chart. Now in order to understand this, you need to have a clear understanding of the derivation of the resistance and reactance circle, as well as the graphical explanation of how Smith chart circles are formed. So this is why I have chosen only these three topics for this lecture. Okay, alright, now let us start with our first topic, which is derivation of resistance and reactance circle formula. We all know that in a transmission line, we attach a load impedance ZL, and the length of the transmission line, let us call it small l. And we look into the transmission line, let us say from this point, and we want to find the input impedance Zin. Let us assume that the transmission line has a characteristic impedance of Z0. This is the basic framework behind which all the question of Smith chart arises. Okay, alright. Now let us start with the derivation. Let us first assume that this load impedance ZL has a real part RL and an imaginary part XL, where this RL is the resistance of load and XL is reactance of load. Now in a Smith chart, the plots are always normalized with respect to the characteristic impedance of the transmission line. That means whenever you plot a load impedance or the input impedance, you always plot normalized impedances. So that is why we are going to normalize our load impedance ZL with respect to the characteristic impedance of the transmission line, which is Z0. So let us do that. So since ZL is our load impedance, so we are going to divide it with the characteristic impedance Z0. So we will get RL divided by Z0 plus J XL divided by Z0. This can be written as RL plus J XL. Notice that this is a small case letter R and this is a small case letter X. So the small case letters represent the normalized resistances and normalized reactance of the load. So we can simply write small ZL is equals to RL plus J XL, where this small ZL is nothing but the normalized load impedance, which is capital ZL divided by Z0. Okay, alright. Now let's move forward. Now we know that the formula for the reflection coefficient is reflection coefficient. Let's call it gamma. So gamma is equals to ZL minus Z0 divided by ZL plus Z0. Okay. Now here also we are going to divide it with the characteristic impedance Z0. So I am going to divide it in the numerator as well as in the denominator. So what you will get? You will get ZL minus 1 divided by ZL plus 1. Okay. Now this formula I am going to use it in just a minute of time. So I am writing it inside a box. Now before using this formula, let us write the reflection coefficient gamma in polar form as well as in complex form. So in the polar form it can be written as mod of gamma into e to the power j theta, where this is the magnitude part of the reflection coefficient and this represents the phase part. Okay, and in the complex form it can be written as gamma r plus j gamma I, where this gamma r is real part of the reflection coefficient and this gamma I is imaginary part of the reflection coefficient gamma. Okay, alright. Now let us use this formula. So this formula can be rewritten as ZL minus 1 is equals to gamma ZL plus gamma, or ZL minus gamma ZL is equals to 1 plus gamma, or if you take ZL common, 1 minus gamma is equals to 1 plus gamma. So ZL becomes equals to 1 plus gamma divided by 1 minus gamma. Now if you substitute the value of the gamma in the phasor form over here, you will get 1 plus mod gamma e to the power j theta divided by 1 minus mod gamma e to the power j theta. Okay, now this is an important relation, so I am going to box this inside. So we are going to use this relation later on when we will compare this with the formula of the input impedance Zin. Okay, alright. Now here we can also replace this gamma with the complex part of the reflection coefficient. So let us do that. Therefore 1 plus gamma r plus j gamma I divided by 1 minus gamma r plus j gamma I. So this can be written as 1 plus gamma r plus j gamma I divided by 1 minus gamma r minus j gamma I. So I am basically arranging the real and imaginary part together. Alright, okay. Now let us rewrite that equation in a fresh page, so that we are going to rationalize it and find the equation of the resistance circle and the reactance circle. So I am going to rationalize it. So this becomes 1 minus gamma r plus j gamma I. In the numerator also 1 minus gamma r plus j gamma I. Okay, so if you do this simple calculation, you will get 1 plus gamma r into 1 minus gamma r plus j gamma I times 1 plus gamma r plus j gamma I times 1 minus gamma r plus j square gamma I square whole divided by 1 minus gamma r whole square plus gamma I whole square. Alright, okay. Now since this j square is nothing but minus 1, So we can just write it as 1 minus gamma r square plus j gamma I times 1 plus gamma r plus j times gamma I 1 minus gamma r minus gamma I square whole divided by this denominator, which is 1 minus gamma r whole square plus gamma I whole square. Alright, now let us separate the real and imaginary parts. So we will get 1 minus gamma r square minus gamma I square plus j times gamma I multiplied by 1 plus gamma r plus 1 minus gamma r. So this plus gamma and minus gamma cancels out. In the denominator we are still left out with 1 minus gamma r whole square plus gamma I whole square. So we are left out with 1 minus gamma r square minus gamma I square minus j times 2 gamma I divided by 1 minus gamma r whole square plus gamma I whole square. Okay, so if you now separate the real and imaginary parts, we will get 1 minus gamma r square minus gamma I square divided by the denominator, that is 1 minus gamma r whole square plus gamma I square minus j times 2 gamma I divided by that same denominator, which is 1 minus gamma r whole square plus gamma I square. So here we had the normalized load impedance. So we know that the normalized load impedance ZL is equals to RL plus JXL, which is equals to these two terms, that is 1 minus gamma r square minus gamma I square divided by 1 minus gamma r whole square plus gamma I square minus j times 2 gamma I divided by 1 minus gamma r whole square plus gamma I square. So this means that RL is equals to this RL is equals to the real part. So that is why RL is equals to 1 minus gamma r square minus gamma I square divided by 1 minus gamma r whole square plus gamma I square. Similarly, the imaginary part XL is equals to this imaginary part. Therefore, we can write XL is equals to minus 2 gamma I divided by 1 minus gamma r whole square plus gamma I square. I am naming this equation as A and this equation as B, small a and small b. Now when you rearrange equation A, you can write it as gamma r minus RL divided by 1 plus RL whole square plus gamma I square is equals to 1 divided by 1 plus RL whole square. Let me call this equation capital A. Similarly, when you rearrange this equation small b, you can find out that it becomes gamma r minus 1 whole square plus gamma I minus 1 over XL whole square is equals to 1 over XL whole square. Let us call this equation capital B. Okay, now these two equations A and B, they resemble the equation of a circle. Therefore, we are going to see this in detail that how the center of this circle and the radius of this circle turns out to form the circles inside the Smith chart. Alright? Okay. Now let me do that. Now you know that the equation of a circle is x minus a whole square plus y minus b whole square is equals to r square, where a and b are the center of the circle and r is the radius of the circle. Okay, let me remove this part. Alright, now if a and b both are 0, that means your center point AB is at the center of the coordinate systems, that is at the origin. So at that time you will get a circle which is centered at the origin of the coordinate system. But if a and b are not equal, that is a and b they are not equals to 0, then in that case your circle will be somewhere, if both a and b are positive, then it will be in the first quadrant of your coordinate system. Alright, now since this is a very basic, using this we are going to understand how the resistance and reactance circles turns out to become the Smith chart. Alright, okay. Now let us look at this first equation, which is equation A. In this equation A, if you see carefully and compare it with x minus a whole square plus y minus b whole square is equals to r square, you will find that a is equals to this and b here is 0 here. So that is why the center of the resistance circle is RL divided by 1 plus RL and 0. So all resistance circle in a Smith chart will have a center on the x-axis and the radius of the circle will be governed by this, that is 1 over 1 plus RL. Okay, so the two important points in this case is, let me choose a different color, that the center of the resistance circle is RL over 1 plus RL comma 0 and radius of the resistance circle is 1 over 1 plus RL. These two is very important. Alright, next move on to the second equation, that is equation B. In this equation you will see that when you compare it with x minus a whole square plus y minus b whole square is equals to r square, you will find that this a is 1 and b is 1 over XL and r is 1 over XL. So all reactance circle will have a center at 1 comma 1 over XL. So the important point to note is that the center of reactance circle is 1 comma 1 over XL and radius is 1 over XL. Okay, these two is very important. Now I have drawn the resistance circle and reactance circle together in a coordinate system. Now in this figure, this red circle is the Smith chart. That means all the circles will be contained inside this red circle only. So basically this red circle is nothing but this entire Smith chart. So if you see this biggest circle, everything inside this biggest circle constitute the Smith chart. Alright, everything inside this. So inside this you have the resistance circle like this, and you also have the reactance circle like this. Let me choose a different color. Okay, so that you have the reactance circles like this, and in the lower hemisphere also. Alright, in order to illustrate that, I have chosen this particular diagram where this blue color circle is the resistance circle and the green color circle is the reactance circle. Okay, so when you look at a Smith chart, you can only see a part of the reactance circle, which is only this curve or this curve. Alright, that is why in a Smith chart these arcs are visible, which represents the reactance circle. Okay, alright. Now let us try to put two different values of RL in this equation. So let us choose the blue color circle first. So we know that for a blue color circle, which represents the resistance circle, has a center at RL divided by 1 plus RL, comma 0, and radius is 1 over 1 plus RL. So when you substitute RL is equals to infinity, the radius of blue circle, which is the resistance circle, goes to 0, and the center is at 1 comma 0. Okay, that means when the load resistance is infinite, then the center of the circle is at 1 comma 0, which is at this point, and the radius of the circle becomes 0, that is, it just becomes a point. That means these circles, which represents the resistance circle, that is the blue color circle, when the radius of these circles becomes so small that it becomes 0, or you can just call it as a point, then that represents that the load resistance is infinite. Okay, similarly, when you put RL is equals to 0, that is the load resistance is 0, the radius of the blue circle becomes equals to unity. That is, when you put RL is equals to 0 here, the radius will become 1, and the center will become, if you put RL is equals to 0, the center will become 0 comma 0. So the center of the circle will be this origin, which is 0 comma 0, and the radius of the circle is unity, that is this entire Smith chart, the biggest circle in the Smith chart. Alright, okay, so the two important points in this case is when RL is equals to infinity, let me choose a different color. When RL is equals to infinity, then the radius of the resistance circle goes to 0, and the center is at 1 comma 0. When RL is equals to 0, then the radius of resistance circle becomes unity, and the center is at 0 comma 0. Alright, similarly, when you put XL is equals to infinity, when you put XL is equals to infinity, let me choose this color. When you put XL is equals to infinity, the radius of the green circle, which is the reactance circle, goes to 0, and the center is at 1 comma 0, which is this same point, when XL is equals to infinity. And when XL is equals to 0, then the radius becomes infinity, and the center is 1 comma infinity. Okay, that means the center of the reactance circle in that case will be, in the x-axis it moves up to this point, and in the y-axis it goes to infinity. the center of the circle, and the radius of the circle is also infinity. So in a small 2D sheet we can only see a horizontal line. So this horizontal line represents xl is equals to 0, because the radius is infinity and you can just see the horizontal straight line. The center goes to 1 comma infinity. Alright, so these are the few important points which you should remember. Alright, now I have just kept this Smith chart to just give you a look that how a Smith chart looks. Now this Smith chart has various scales such as resistance component and conductance component, wavelength towards the generator, angle of reflection coefficient and angle of transmission coefficient. It has scales such as SWR in linear scale, return loss in dB, SWR in dB, reflection coefficient in terms of power, and reflection coefficient in terms of the voltage and current. Similarly, attenuation in dB, reflection loss in dB, transmission coefficient in terms of power, transmission coefficient in terms of voltage and current. These are various scales in a Smith chart. I have explained this measurement scale of Smith chart in great detail in a different video, which you can watch it in the playlist of this lecture. So I am not going to go in detail regarding the measurement scale of this Smith chart, but you can watch that video. That will be very helpful for you. Alright, now I am going to move on to the next agenda of this lecture, which is understanding the load impedance and the input impedance using Smith chart. Okay, before that we need to first derive the formula for the input impedance in terms of the reflection coefficient. So derivation of Zin as a function of reflection coefficient. So we know that Zin is equals to Z0 into ZL plus JZ0 tan beta L divided by Z0 plus JZL tan beta L. Okay, now if you divide numerator and denominator with respect to the characteristic impedance, you will get ZL by Z0 plus J times Z0 by Z0 tan beta L whole divided by Z0 by Z0 plus J times ZL by Z0 tan beta L. So this can be further written as Z0 times, so this becomes small ZL, that is the normalized load impedance, plus J times tan beta L, and here it becomes 1 plus JZL times tan beta L. Okay, now since we know that this ZL is nothing but 1 plus gamma divided by 1 minus gamma, so I am going to substitute that. So we will get 1 plus gamma divided by 1 minus gamma plus J times tan beta L divided by 1 plus J times 1 plus gamma divided by 1 minus gamma into tan beta L. Now if you simplify this, you will get 1 plus gamma plus J times tan beta L minus J times gamma tan beta L whole divided by 1 minus gamma divided by 1 minus gamma plus J times tan beta L plus j times gamma tan beta L divided by 1 minus gamma. So this 1 minus gamma and 1 minus gamma cancels out, and you are left out with 1 plus gamma plus 1 minus gamma times j tan beta L divided by 1 minus gamma plus j times 1 plus gamma into tan beta L. So this now, since there is one small formula I am going to give you, that j times tan beta L can be written as e to the power j 2 beta L minus 1 divided by e to the power j 2 beta L plus 1. So I am going to use this formula and substitute it in this term. So the formula will become 1 plus gamma plus 1 minus gamma times e to the power j 2 beta L minus 1 e to the power j 2 beta L plus 1 whole divided by 1 minus gamma plus 1 plus gamma into e to the power j 2 beta L minus 1 divided by e to the power j 2 beta L plus 1. So when you simplify this, you will get 1 plus gamma into e to the power j 2 beta L plus 1 plus 1 minus gamma times e to the power j 2 beta L minus 1 whole divided by 1 minus gamma times e to the power j 2 beta L plus 1 plus 1 plus gamma times e to the power j 2 beta L minus 1. Alright, now if you expand this, you will get e to the power j 2 beta L plus gamma times e to the power j 2 beta L plus 1 plus gamma plus e to the power j 2 beta L minus gamma times e to the power j 2 beta L minus 1 plus gamma whole divided by e to the power j 2 beta L minus gamma times e to the power j 2 beta L plus 1 minus gamma plus e to the power j 2 beta L plus gamma times e to the power j 2 beta L minus 1 minus gamma. So here minus gamma e to the power j 2 beta L and plus gamma j e to the power j 2 beta L cancels out. This plus 1 and minus 1 cancels out. Similarly here also these terms cancels out. So you are left out with 2 times gamma plus e to the power j 2 beta L divided by 2 times minus gamma plus e to the power j 2 beta L, which can be written as these two cancels out. So 1 plus gamma e to the power minus j 2 beta L divided by 1 minus gamma e to the power minus j 2 beta L. This is your input impedance ZIN. Alright, now we are in a position to compare the two equations. Alright, so I am going to first write the equation of the load impedance in terms of the reflection coefficient. So the load impedance is ZL equals to 1 plus mod of gamma e to the power j theta divided by 1 minus mod of gamma e to the power j theta. We have derived this equation earlier. you can check that. Similarly, recently we have just derived the formula for the input impedance, which is Zin is equals to Z0 times 1 plus gamma e to the power minus 2j beta L divided by 1 minus gamma e to the power minus 2j beta L. Okay, I think I have forgotten to write Z0 here. So in this formula, Z0 is present everywhere. All right. So now we have these two equations. Let me call it this as equation 1 and this as equation 2. Okay, so whenever we plot a Smith chart, now this is the most important thing which is necessary to solve a Smith chart question or a transmission line question. So we have the real axis and the imaginary axis. So the real axis is gamma r, the real part of the transmission, the real part of the reflection coefficient, and the imaginary axis is gamma I, which is the imaginary part of the reflection coefficient. And let us say we have a Smith chart circle. Let me reposition it at the center. So this is our Smith chart circle. Now suppose you know the value of gamma, that is the mod of gamma into e to the power j theta. So you know mod of gamma. So you have drawn the circle of reflection coefficient. Let me reposition it at the center. Yeah. So this is the circle of reflection coefficient which you have drawn it since you know the value of the magnitude of the reflection coefficient. And since you also know the value of theta, so you have pointed out a point here which represents the load impedance ZL. Why? Because once you know gamma and e to the power j theta, you know ZL. So this particular point represents the normalized load impedance in a Smith chart. So in order to find the input impedance, what you just need to do is that you move in the clockwise direction by an angle of theta is equals to 2 beta L. That is, suppose you have a transmission line and you have a ZL load impedance and you want to find out the input impedance looking at from this point, and you know the length of the transmission line, which is L. So if you just move in the clockwise direction by an angle of 2 beta L, you can reach, let us say you reach at this point. So this point will represent your Zin. Why? Because this point was telling you impedance at load. So when you move away from the load towards the generator, you basically move in the clockwise direction. Therefore, if you move by an angle of 2 beta L, you will reach a point. Let us say you reach at this point. So that point will represent the input impedance of the transmission line looking at a length L away from the load ZL. Alright, so just by looking at this formula, you understand that this theta and this 2 times beta L tells you the relationship between ZL and ZIN. Okay, so therefore these two relations tells you how in a same reflection coefficient circle you can find the load impedance as well as the input impedance just by moving an angle of 2 beta L in the clockwise direction. Okay, I hope this concept is clear to you, because this is one of the most important thing which usually is asked in a GATE question. So I hope you have understood this. If you have any doubts, please type it in the comment box. I will be very much happy to answer your questions. In the next lecture, I will try to solve few MCQs which are based on Smith chart, which may probably come in a GATE exam. Thank you very much. I'll see you in the next lecture.